Okay, so you might recall from our previous video that the derivative is the slope of the line tangent to the graph at any particular point. We also took a look at when the slope of the tangent line would be 0. Those are going to become critical values later on when we apply our derivative. Remember that we had horizontal tangent lines, or horizontal lines have a slope of 0. In this video, we're going to take a look at what happens when they have vertical tangent lines. Remember, with a vertical line, if we had a vertical line, this has what we call a no slope or an undefined slope. And the way to remember that is two vertical lines form the letter N, hence the word no slope or an undefined slope. So what ends up happening with our derivative stuff is that where the derivative is undefined, that's where you're going to have a vertical tangent line. Theoretically, or when you put it into the proper notational form, you will say that a vertical tangent line occurs, or the definition of vertical tangent line, you'll say that a graph, say F, has a vertical tangent line at x equals a if the original graph F is continuous at a and if the limit as x approaches a of the absolute value of the derivative of the function goes to infinity. The absolute value of the derivative. So you can go positive infinity or negative infinity. But the practical, in all practical purposes, the easier way of looking at this is saying, okay, well, when am I going to have a vertical tangent line is where my derivative is not defined. So let's take a look at an example of that. Let's say we had something like the original function f of x equals x to the 2/3 power. X to the 2/3 power is a seagull looking type graph. So it comes down like this, touches at 0, and keeps on going. It's continuous over all real numbers. You're taking the cube root of x squared, so it is continuous. You don't have to worry about that piece of it. If we were to take the derivative of that, f prime of x, what I would get is 2 over 3x to the 1/3 power, and that's a 1/3. Notice that at 0, that derivative would not be defined. So therefore, it has a vertical tangent line at x equals 0. If you do it theoretically, you say, okay, well, the limit as x approaches 0 of the absolute value of 2 over 3x to the 1/3 goes to infinity. Therefore, we have a vertical tangent line at x equals 0. A second concept that is related to this is called a cusp. And a graph is going to have a cusp. First of all, it has to have a vertical tangent line. A graph has a cusp. At x equals a, if f is continuous, at a, and these two things have to be true. Number one, f prime of x has to go to positive infinity as x approaches as x approaches a from one side, and from the other side f prime of x has to approach negative infinity as x approaches a from the other side. I'll put a little superscript positive and negative. Those could be switched around, but if I go back to my original example, from f of x equals f prime of x equals 2 over 3x to the 1/3, and the graph of that derivative would look something like this. If I were to graph the derivative, remember this is the plot of the derivative, not the original function. The original function I drew a few minutes ago. Now, as x approaches a from the left-hand side this way, it's going to negative infinity, but as x approaches 0 from the right-hand side, it's going to positive infinity. So we would say that if f of x equals x to the 2/3, there is a cusp at x equals 0. Our final concept here today is called normal lines, and a normal line is perpendicular to the tangent line at any particular point along the graph, so at x equals a. The concept there is that it's just a perpendicular. We don't use normal lines quite as much as we used to. What ends up happening is that, let's say I had something like function like this. Let's say I had f of x equals x squared minus 3x plus 1, and I have the point f of 1 equals negative 1. That point falls on the graph. Okay, so the derivative of this function, f prime of x, is equal to 2x minus 3. F prime of 1 is equal, put 1 in here and I get negative 1. So if I were to write the slope of my tangent line, that would be negative 1. The slope of my normal line would be perpendicular to this, which would be the opposite reciprocal, or positive 1. So if I went ahead and I wanted to write my equations of my my normal and tangent line, I could write those and I could do them in point slope form. For the tangent line, it would be y plus 1 equals negative 1 times x minus 1. For the normal line, it would be y plus 1 equals positive 1 times x plus 1. So again, we're starting to apply some of our derivative stuff here. We're starting to get into tangent lines and normal lines and vertical tangent lines and cusp and all that stuff. A cusp is a BC objective. It's not an AB objective. It will not be on your AB exam, but I will ask you about it on your test and quizzes, and some extra problems that kind of fits in right here with this. Okay, good luck on the assignment.